For this class, we're identifying wavelengths and frequencies of different colors of in the rainbow, which is just visible light. So we could choose any frequency and arrange for a given color. So for example, red light, one of the frequencies we could choose is 4 times 10 to the 14 hertz, because if you look at your electromagnetic spectrum chart, that falls in the range for red light. So we start with V equals F lambda. V, remember, is 3 times 10 to the 8th meters per second. That's the speed of light. F, we just chose 4 times 10 to the 14 hertz. Now remember, that can be different than one of your friends because we just chose this number. They could have chosen another number in that range, times lambda. Dividing both sides by 4 times 10 to the 14 hertz, and just be careful here when you do the division in your calculator. A lot of students forget to put parentheses around the second number when they divide. You should get about 7.5 times 10 to the negative 7 meters. And that would be our wavelength there. Now, I am not going to do all of these. All right, you should work on these on your own and practice them. But one thing I'll say is that all of these should come out something 10 to the negative 7 meters, every single one. The other thing you should notice, and why don't we write it, actually, yeah, why don't we write it up on top here, off to the side. So as we go from red to violet, you should have noticed that your frequencies went up, but your wavelengths gradually went down. So 7.5 times 10 to the negative 7 meters should be your greatest wavelength. When you get all the way to violet, it should be like 4 point something or so. And all of your frequencies should go up. Red has the lowest frequency, violet would have the highest frequency. All right. So just some practice questions. This one says an AM radio wave could have a wavelength of. Now, if you look at your electromagnetic spectrum chart, you would notice that AM radio waves are anywhere from 10 to the second meters or 10 to the third meters. So between 100 and 1,000, that only leaves us with one choice right here, 5 times 10 to the 2 or 500 meters. Finding the frequency, we'll go back to V equals F lambda. Remember, this is light, so we know V. It's 3 times 10 to the 8th meters per second. F is our unknown, and our wavelength is 500 meters. Divide both sides by 500 meters. And we get about 600,000 hertz. The next one says, which color of light has a wavelength of 5 times 10 to the negative 7 meters? Hint, find frequency first. If you look at your colors, you'll notice that you can't really distinguish them by wavelength. It only gives it to you on your equation sheet by frequency, so you got to convert to frequency first from wavelength. So again, we're using V equals F lambda. V is 3 times 10 to the 8th. Frequency is unknown, and we have 5 times 10 to the negative 7 meters. Divide both sides by 5 times 10 to the negative 7. Again, just be careful. A lot of students make mistakes here. All right, you have to use parentheses around each of your numbers when you divide them, unless you set it up in your calculator as a fraction. Please be careful. You have to practice this. A lot of students are going to make mistakes on the exam if they don't practice this now. Here you get 6 times 10 to the 14 hertz. And that corresponds to green. The next question says, an electromagnetic wave traveling through a vacuum has a wavelength of 1.5 times 10 to the negative 1 meters. That's the same as 0.15 meters. What is the period of this wave? Hint, find the frequency first. So V equals F lambda, we got to find the frequency. We don't have the period, we have to find the period. 3 times 10 to the 8th. I'm going to leave the units out to keep things a little compact. F is my unknown, and my wavelength is 0.15. And you should get a frequency of 2 billion, 2 times 10 to the 9 hertz. Now how do we turn that into period? Period equals 1 over frequency. So period equals 1 over 2 times 10 to the 9. So let's see what we get there. I think we get 5 times 10 to the negative 10 seconds. So a really small amount of time. And that makes sense. If our frequency is 2 billion, that means it's oscillating up and down 2 billion times a second. So if the period is the time for one oscillation, it's got to be a really small number. The next one here says sunlight is composed of various intensities of all frequencies of light. The graph represents the relationship between light intensity and frequency. So this is from our sun. So let's see, we have visible light here. So the smallest frequency would be over here. The lowest frequency of visible light is red. So this is red light up here. The highest frequency of visible light is violet. Somewhere in the middle here, that's like yellow or orange. Now that should make sense to us that that's the most intensity because our sun kind of looks like a yellowish orange color. So which one has the least intensity? That would be violet. Notice how it has the lowest amount of intensity. Intensity is on the y-axis. Next one here says, what is the wavelength of this wave, or of the wave above? Let's see how many waves there are. So we have 1 wave, 2 waves, 3 waves. So a lot of people will be tempted to say that the answer here is 1.5 times 10 to the negative 6 meters, but we know that that is not a wavelength. A wavelength is the length of 1 wave. So if that total length is the length of 3 waves, how much is each wave? So let's see, 3 lambda, 3 wavelengths equals 1.5 times 10 to the negative 6 meters. Dividing both sides by 3, we get 5 times 10 to the negative 7 meters. So basically you just divide by 3. So this next one is connected. It says, what is the frequency of the light? So if we have the wavelength of light, what we need to do is then use V equals F lambda to get the frequency. So V equals F lambda. V is 3 times 10 to the 8th. F is our unknown, and our wavelength is 5 times 10 to the negative 7. We should have units in there, I'm just leaving them out now. Dividing both sides by 5 times 10 to the negative 7, we get 6 times 10 to the 14 hertz. What color does this correspond to? Green. It's just a coincidence that most of these are green. On a test or a quiz, it can be something else. Compared to the period, so this is a new question now. Compared to the period of light, compared to the period of a wave of red light, the period of a wave of green light is, so what a lot of students did for this one was they chose numbers. So they chose a frequency in the red light spectrum and a frequency in the green light spectrum and found the periods for both and answered it that way. So another way to do it is to just look at the frequencies and kind of compare. So it looks like to me that red has a lower frequency of light than green. So let's just make note of that. Red has lower F than green. And we know, so that's the first point, we know that frequency is inversely proportional to period. Therefore, red has a higher period than green. So red has a higher period, or a longer period. So let's read what the question says. Compared to the period of a wave of red light, the period of a wave of green light is lower, because we just said red has a higher period. So that's a tough question, because you have to understand the relationship between frequency and period, and you also have to be able to read the electromagnetic spectrum chart. The next one here says, how much time does it take light from a flash camera to reach the subject who is 6 meters away across the room? So I give you a hint, use distance equals velocity times time. So I'm just going to show the setup for this. 6 meters is our distance. Our velocity, again, it's light. So 3 times 10 to the 8th meters per second. And that's equal to, not equal to, but multiplied by time. So you're going to divide both sides by 3 times 10 to the 8th meters per second. You should get a really small number. You should get 2 times 10 to the negative 8 seconds. So it takes a really small amount of time for the light to get across the room, which makes sense because it's moving really fast. The next one says an electromagnetic wave is produced by charged particles vibrating at a rate of 3.9 times 10 to the 8th vibrations per second. The electromagnetic wave is, so you have to just recognize that this means frequency. That's the frequency. It's the same thing as saying hertz, 3.9 times 10 to the 8th hertz, because a hertz is an oscillation per second or a cycle per second. And it looks like, if we look at what frequency that falls under, we're looking at the bottom of our chart, the bottom row. It looks like that falls in the radio wave portion of the scale.